I'm Dr. Shweta Sharma from ABES Engineering College, Ghaziabad. In this lecture, I'll discuss about the IR spectroscopy. I will discuss these mentioned contents in the lecture about the introduction, principle and regions of IR spectroscopy, about the fundamental vibrations of IR spectroscopy, instrumentation and applications of IR spectroscopy, and some questions related to IR spectroscopy. So, what is IR spectroscopy? Basically, it is also known as vibrational spectroscopy. And why it is called as vibrational spectroscopy? Because every bond in a molecule like vibrates at its mean position, and it behaves like a tiny magnet. This bond vibrates at a particular frequency, and this frequency is calculated by the Hooke's law, which is 1 upon 2 pi c root k by nu. K is the force constant of the bond, and which is directly proportional to the strength of the bond. Force constant tells about the strength of the bond, and it also tells about the stiffness of the bond. Nu is the reduced mass. Reduced mass can be calculated for a bond AB for a diatomic molecule by reduced mass is Ma into Mb. Ma is the mass of atom A and Mb is the mass of atom B divided by Ma plus Mb. So basically each bond vibrates at its mean position, and this frequency of vibration is calculated by the Hooke's law. And IR spectroscopy deals with the interaction or transitions between these vibrational energy levels of a bond when a molecule absorbs the radiations falling in the IR range and which correspond to value 4000 centimeter inverse to 400 centimeter inverse. So when vibration occurs, vibrational energy levels are associated with it. And when molecule undergo transitions between these vibrational energy levels on absorption of IR radiations, we study this as IR spectroscopy. That's why this spectroscopy is also known as vibrational spectroscopy, because here we are concerned about the vibrational motion of any molecule. So what is the selection rule for IR spectroscopy? The basic selection rule for IR spectroscopy is that the net dipole moment of any molecule during vibration should be non-zero. If a net dipole moment for any particular molecule during any vibration is non-zero, then this molecule is said to be IR active molecule or IR active compound. IR active compound means the molecule, its IR spectrum can be recorded. For example, the molecules having permanent dipole moment or net dipole moment non-zero is hydrogen chloride, HCN, CO2. These are the molecules which have net dipole moment non-zero during any of the vibrations. If the molecule has net dipole moment 0, it's said to be IR inactive. Its net dipole moment is 0. It is IR inactive molecule, which means that it will not record IR spectrum. For example, molecules like O2, nitrogen molecule, chlorine molecule, these molecules have net dipole moment 0 and they are IR inactive, means their IR spectrum cannot be recorded. Next is the regions of IR spectroscopy. As I mentioned that IR spectral range, which we study for vibrational energy level transition, correspond to 4000 centimeter inverse to 400 centimeter inverse. This region is divided into the three main region. First is the functional group region. Functional group region correspond to 400 centimeter inverse to 1400 centimeter inverse. And this region provides information about presence of particular functional group in the molecule, because every functional group or particular functional group has a specific value of fundamental vibration which corresponds to that uh, functional group only. For example, if we talk about the simple and some basic functional groups, carbonyl group, it has fundamental vibrational frequency corresponding to 1800 to 1450 centimeter inverse. OH molecule, hydroxyl group, has frequency 3600 centimeter inverse to 3450 centimeter inverse. CH stretching frequency, stretching vibration frequency, which is the part of all hydrocarbons, is corresponds to 2980 centimeter inverse to 2800 centimeter inverse. So these are some basic functional groups which have their particular frequency vibration, and presence of any such band in the spectrum correspond to the presence of these functional group in the molecule. Second region is the fingerprint region. Fingerprint region gives information about presence of isomers in the sample. Fingerprint region corresponds to 1400 centimeter inverse to 900 centimeter inverse in the frequency band. This band gives information about the isomers in the molecule, because this band can provide information about each and every isomer present in the sample, just like the fingerprints are our fingerprints are our identity. In the similar way, the bands in this region is the identity of the particular isomer present in the sample. These isomers can be structural isomers, or they can be stereoisomers, structural as well as stereoisomers. Third region of eye spectroscopy, or this region, is aromatic region or low intensity region. Aromatic region or low intensity region, which corresponds to 900 centimeter inverse to 400 centimeter inverse. The presence of band in this region gives information about the presence of aromatic molecule in the sample. These bands are aromatic compound or aromatic sample. These bands are of very low intensity, not very sharp, and they appear blur in the spectrum. They appear little bit low intensity and blur in the spectrum. So these are the regions of IR spectroscopy. Now let's discuss the fundamental vibrations of IR spectroscopy. There are two types of fundamental vibrations: stretching vibrations and bending vibration. I'll be first discussing about the stretching vibrations. Stretching vibrations means the expansion and compression of a bond. Bond is stretching and bond is compressing. These stretching vibrations can be symmetrical stretching or asymmetrical stretching. Symmetrical stretching or asymmetrical stretching. Symmetrical stretching means when the net dipole moment or the bond is expanding equally in all the direction. If I'll take the example of linear molecule like carbon monoxide, this is carbon monoxide. Carbon dioxide molecule, carbon dioxide Carbon dioxide molecule can expand in both the direction or in both bonds expand equally. If it also happened that both bonds can compress equally. In both the situations, net dipole moment is zero. In both the situations, net dipole moment is zero. So this vibration of carbon dioxide is IR inactive because bond is compressing and expanding in both bonds equally. And if I'll talk about the asymmetrical stretching of carbon dioxide, one bond is expanding and another bond is compressing. In this situation, the net dipole moment is non-zero because there is non-equivalent expansion and compression in the bond. This is the asymmetrical vibration. In this situation, net dipole moment is zero. In non-zero, net dipole moment is not equal to zero. This asymmetrical stretching vibration of carbon dioxide is IR active. So, stretching vibrations is of two types, symmetrical stretching and asymmetrical stretching. I have just mentioned or taken the example of carbon dioxide, in which I have shown that asymmetrical stretching vibration of carbon dioxide molecule, net dipole moment is non-zero, is IR active. Next is a bending vibration. In bending vibration, there is two types again. In plane bending, molecule is bending in its own plane, in plane bending, and we have out of plane bending. Molecule is moving out of its plane while bending. Out of plane bending and in plane bending. In plane bending, we have rocking vibration and scissoring vibration. I'll take example of water molecule. This is water molecule. During rocking, both bonds move in a same direction, or they can move like this also. So water molecule, both the bonds are moving in the same plane or vibrating in the same plane. In scissoring vibration, it is again vibrating in the same plane, but in this manner. Just like the two blades of a scissor, this is scissoring vibration. Both the bonds are vibrating opposite to each other. Out of plane bending, we have wagging vibration and twisting vibration. In wagging vibration, both the bonds are out of the plane in the same manner. This is two types of wagging vibration in which this positive sign shows that both the bonds of water molecules are coming out of the plane or vibrating above the plane. Both the negative sign shows that both the bonds of the water molecules are vibrating below the plane of the molecule. So here, both bonds above the plane, both bonds below the plane. In twisting vibration, bonds vibrate alternatively. For example, again water molecule, plus sign, and here we have minus. This shows that one bond is vibrating above the plane and other bond is vibrating below the plane. Just like the two steps of a twist or twist dance, these bonds are vibrating in a alternate manner. So this is the bending vibration and the stretching vibrations or fundamental vibrations of IR spectroscopy. Next, we can calculate the number of vibrations of the IR spectroscopy for linear as well as non-linear molecules. For linear molecules, for example, ethene, C2H2, ethine, or carbon dioxide, these are the linear molecules, ethine and carbon dioxide. Linear vibrations are calculated by formula 3n minus 5, where n is the number of atoms present in molecule. Number of atoms in a molecule. So for the ethine, this is 3 into 4 minus 5. There are 7 vibrations. For carbon dioxide, this is 3 into 3 minus 5. 4 vibrations, 4 fundamental vibrations in IR spectroscopy for carbon dioxide molecules, which are IR active. And for ethine, there are 7 fundamental vibrations in the IR spectrum. For non-linear molecules, we can calculate the vibration by the formula 3n minus 6. 3n minus 6, where n corresponds to the number of atoms present in the molecule. If I'll take an example of non-linear molecule like methane, benzene, water molecule, they all are non-linear molecule. 3n, this is n correspond to the number of atoms in the molecule. 3 minus 3 to 5 minus 6, that is the 9 vibrations for methane molecule. 3 into 12 minus 6, 30 vibrations for benzene molecule. And we have 3 vibrations for water molecules, which are IR active. If I talk about the instrumentation of IR spectroscopy, we have a source of radiation. For IR spectroscopy, radiation source is a nursed glower, which usually operate at 1500 degrees Celsius, and it releases the IR radiation. Nursed glower operates at 1500 degrees Celsius, and we have a dispersing element which is rock salt prism. It is rock salt prism. And we have a detector which is a thermocouple. It is a detector which is a thermocouple. So these are the basic instrumentation parts of the IR spectrophotometer. We have a source of radiation, and this is a beam attenuator. And it goes to the sample, this beam attenuator, as well as it is placed to the reference compound. It is taken as the reference compound. This beam is then detected by the detector. It is amplified with the help of amplifier. And then we have our recording system to detect it or record. In this manner, IR spectrum is recorded with the help of IR spectrophotometer. The most important applications of IR spectrum or IR spectroscopy is to determine the functional group or determine the functional group in the molecules. Because every bond or every functional group has a specific frequency at which it vibrates, and this frequency provides information about the presence of a specific functional group in the molecule. We can determine the purity of the sample by using IR spectroscopy. We can determine the force constant of a bond. This force constant of the bond provides information about the stiffness of the bond and the strength of the bond. We can determine the hydrogen bonding with the help of IR spectroscopy. IR spectroscopy gives information about both intermolecular and intramolecular hydrogen bonding present in the sample. We can determine the dipole moment with this IR spectroscopy, bond length, and strength of the molecule with the IR spectroscopy. So, question about the IR spectroscopy is that if we have a compound having formula C3H6O, this compound give the following bands or these bands in the IR spectrum corresponding to 1720 centimeter inverse and a one bond corresponding to 2980 centimeter inverse. While during IR spectrum, these two bands are observed for compound having formula C3H6O. Also, the given compound show negative tolerance test in the IR spectrum. Negative tolerance test. So these are the fundamental vibrations and the chemical test result available to detect the structure of the compound having formula C3H6O. So first of all, we will detect first of all, it is required to identify the band observed in the spectrum. 1720 centimeter inverse band corresponds to the carbonyl group because this value lie in the range of the carbonyl group as I have discussed in the functional group region of the spectroscopy. 2980 centimeter inverse corresponds to the CH stretching band of IR spectroscopy or this functional group region, CH stretching frequency. On the basis of these two bands, two structures can be drawn or two structures are possible. One is the ketone or propanone and another structure is an aldehyde. These two structures correspond to C3H6O and both correspond to the presence of carbonyl group and both corresponds to the presence of the CH stretching band in the spectroscopy. And if we took a look at the negative tolerance test, it suggests that the given compound or the given sample is propanone, not the propanol. This is the molecule propanone. Propanol is not present because tolerance test is negative. Therefore, there is no probability of presence of aldehyde. So given compound is a ketone propanone, not the aldehyde. In this way, we can detect the structure of the unknown sample by using the IR spectroscopy. If I'll take one more example, we have the molecule giving the formula C2H4O2. The IR absorption bands corresponding to this molecule are or this sample are 2900 centimeter inverse and 1710 centimeter inverse and one more band which corresponds to 3500 centimeter inverse. These are the three bands which are given for this sample. First of all, we will identify these bands. Also, the test for the chemical result of chemical test is also given. The compound give brisk effervescence test. It give brisk effervescence test with sodium bicarbonate. First of all, we will identify the bands. 2900 centimeter inverse correspond to the CH stretching vibration. 1710 corresponds to the presence of carbonyl group in the sample. 3500 centimeter inverse correspond to the presence of OH group in the sample. Brisk effervescence test with sodium bicarbonate suggests the presence of carboxylic group in the sample. And by this formula, The carboxylic group we can write is the acetic acid or ethanoic acid. This is C2H4O2. This compound has CH stretching, carbonyl group as well as the OH group present in them. Therefore, the compound is ethanoic acid. In this way, we can determine the structure of the unknown compound, or we can do the structure elucidation or functional group identification with the help of IR spectroscopy. These are reference. Thank you, all of you.